Okay, so welcome back to part 2 of the forces unit. And just to remind you, we're starting the forces unit by revisiting motion, another aspect of motion. So in the first lesson, we learned a little bit about what acceleration is, how it's defined scientifically. Remember, it's a little different. So acceleration can include not only getting faster, but also getting slower, and possibly even changing direction. Now I want to look at what acceleration would look like on a position time graph and how we could calculate acceleration from a position time graph. We saw a little of this in the motion unit when we talked about velocity on a position time graph. But I want to show you some graphs, some shapes of position time graphs that would describe acceleration. Okay, so let's do this way. What would getting faster look like if we were to graph position and time? So I want to remind you that on a position time graph, the speed is seen as the slope of the graph. So the more slopey the line is, the more speedy the object is. So with getting faster, we have to have a graph that's getting more slopey as we move across in time. So that could look two different ways. So if this is position and this is time, one way to get slopier is to go like that. See how it's curving? All right, so it's faster at the end than at the beginning. Well, there's another way to get faster, because if you're moving backwards, let's label these here. This is position, this is time. If you're moving backwards, we'll be getting like that. Okay, notice in both cases getting steeper. Now if you're getting slower, then just the opposite happens. That means the line will get less steep. So two ways to see that, depending on which direction you're going. So one would be, if you're moving forward, so it's curved like that. The other possibility is, if you're moving backwards, something like that, okay? So you cannot have a straight line. If you have a straight line, it's a nice steady slope or a steady speed. So we have to have something with a changing slope to see getting faster or slower. Now, when we graph position and time, we cannot see changing direction in situations like this, just the getting faster or slower part. So let's do an example now where we could calculate the acceleration based on the information given on a position time graph. Okay, so we're going to do another calculation of acceleration, much like we did in the first lesson. But if you remember in the first lesson, I simply gave you the initial speed and the final speed, and then how long it took to change from the initial up to the final, or perhaps from the initial down to the final if it was getting slower. But we could also see that on a position time graph. And so I want to point out the one key thing that will be different here. The key to this is to use the slope of the graph to find the initial speed and the final speed. You see, I'm using the word speed even though I write v, because it doesn't really matter in this case whether we distinguish between velocity and speed. All right, so let's look at a position time graph, and we'll see how we could calculate the acceleration while it changes its speed. Okay, I'm going to show you a little image of one of those. Now, unfortunately, this isn't something you're going to easily be able to draw into your notes, and I'm not going to try either. So you're going to have to kind of tune in and refer back to this diagram, this graph, as we do our work here. So let me describe what we're seeing here, and I'll use my mouse. So for the first 4 seconds or so, this is an object that has a pretty steady speed. You see how the slope doesn't change over the first 4 seconds? But then we get some curvature, and that's that curvature I was referring to a moment ago. See how it's getting less slopey? That means it's getting less speedy. So from about 4 until 6 seconds is when we're changing speed. And then we're steady again. And of course, how steady is that? Well, this is a flat position time graph, which means there's no motion at all. This is something that has stopped by the time we reach 6 seconds until the end of this 10 seconds shown here. So what I'm going to do now is calculate the acceleration during the 2 seconds where it changed its speed, from 4 up to 6 seconds on the clock. Okay? So here's what we'll do. We're going to write our formula for acceleration, and then we'll come back to the graph to see what we need from the slopes of that. Okay, so as always, we start with the symbols. And this is the very definition of acceleration. Vf, the final speed, minus Vi, the initial speed. You do all that first, and then divide it by the amount of time it takes to change the speed. Now on this graph, there's a lot of times there. I want to make sure you know which time to include in this formula. Okay? So what we're going to do is we're going to go back to the graph. We're going to figure out the speed that it started with over the first few seconds, and the speed that it ended with, which we already know because I pointed out that it ended up stopped. Okay? So I'm going to put 0 there. 0 slope is pretty easy to recognize. And then we'll go also while we're there and get the time. Okay? So let's take a look at the graph here. All right, so the initial speed is the slope over this nice straight line part from 0 to 4 seconds. Okay? So what I like to do on my paper is I like to do what I call a little bit of corner work. All right? How to calculate the slope. So notice here the slope would be, I call it rise over run. The rise is how far the graph goes up, and the run is how far it goes over between any 2 points. And I'm going to use the beginning and 4 seconds to get that initial velocity. Okay, so I'm going up 20 meters and over 4 seconds. Okay, so 20 meters over 4 seconds. All right, that's how we get the initial speed. All right, so let's go back and we'll write this down. Again, a little bit of corner work. This is not part of our acceleration calculation yet. What we're doing here, we're saying Vi equals the slope, which is 20 meters over 4 seconds. I'm doing this and encouraging you to do it because if you're in the classroom here, teacher needs to kind of tell where you're getting your numbers from. So 20 divided by 4 is 5. The units are meters over seconds. So that means our initial speed was 5 meters per second. Okay? Now, unless you draw this on your paper, it's not going to make much sense on your notes. You're going to have this video to kind of refer to while we're doing this. All right, so back to the graph, because we need to figure out how long it took to change from 5 meters per second down to being stopped. All right? Now again, and I actually, you can probably tell if you look closely, I doctored this graph up a little bit. So I put the curvature starting right here at 4 seconds, and then it was all done curving right around 6 seconds, and then it's flat again. So it took 2 seconds for that speed to change. 2 seconds. So we only use the 2 seconds down here. We're not using the 4 seconds that we were going a steady speed at the beginning. We're not using the 4 seconds that we were going nowhere at all for the last 4 seconds. We're using the 2 seconds during the change. All right? So you'll have to kind of tune into that. All right, order of operations says we take 0 minus 5, that gives us negative 5. We divide it by 2, and that gives us negative 2.5. And then the units that go with it are meters per second divided by seconds. You can call it meters per second, but the better way to write it in a science class is meters per second squared. The squared just goes with the seconds. It's not with the meters. You say it that way, meters per second squared. Like to box the answer when we're done so we can kind of tell that we're done. All right? Okay, so there's an example of how we use the slope at 2 different points on the graph. Again, I'll go back here. We had to use the slope for the beginning part and the slope at the ending part. That was easy because it was 0. And then we divided by how long it took to change that slope, okay? In this case, 2 seconds. So you'll have something very similar to figure out for the practice that you do here, all right? Okay, go back and play whatever you need to. Hopefully this was pretty good for you to see the basics, and we'll get on with a little bit of practice then. Thanks for watching.